In this video, I'm going to focus on vectors, first looking into the basic ideas. What is a vector? I would define it as an arrow that is used to describe anything that has both a magnitude and a direction. Looking at sample vector A, its magnitude or its amount is proportional to its length, and its direction is obviously which way the vector points, in this case east. Looking at sample vector B, this has a smaller magnitude due to its shorter length, but it points in the same direction. Comparing vectors and scalars, vectors again are those that have magnitude and direction. Something you'll find in physics that's a vector is force. We need to know how much the person pushes, 10 newtons, and also which way, to the east. So for vectors, we want to make sure we know how much and which way. Scalars, on the other hand, have magnitude only. Temperature is a good example. 72 degrees is the magnitude, but there's no direction associated with a scalar. Looking at vector directions, we want to consider a north, south, west, east grid. Let's put a vector on there, in this case the blue one. And some students, if asked to describe its direction, would say northeast. And, that's in a way accurate, but that can be a little vague too. Well, why is that vague? I can put other vectors in this quadrant that can also be described as northeast, but that doesn't help differentiate one of these versus the others. So what can we do about that? Adding in angle measurements is a way to be more exact with how we express vector directions, and we just want to make sure we state them in the right way. So zooming in on that, if I were to choose the 40-degree angle, this 40-degree angle is connected to east, so I would write it or state it as 40 degrees north of east. I can also choose the 50-degree angle, and this is connected to north, so I could state that it's 50 degrees east of north. Either of these state the overall direction of the blue vector. Next, let's look at vector addition. I'll start with the easiest example, which is two vectors that point in the same direction, in this case 5 east and 4 east. I want to add them in what's known as the tip-to-tail method, meaning that the tip of my first vector, the red one, touches the tail of my second vector, the blue one. And now to find an answer, I want to connect the beginning of the first to the end of the last, and that would be the purple vector, which would be my answer. So vectors in the same direction, we want to add them together. Now let's look at two in opposite directions, 5 east and 2 west. I start the same way. Tip to tail shows that the tip of red touches the tail of blue. But now, when I connect the beginning of red to the end of blue, I'm going to find that it's a shorter vector. This purple one would end up being my answer, and when you see vectors in opposite directions, you're going to end up subtracting them. A more complicated scenario is when they're on different planes. Now I have 5 east and 3 north. You can't just add them together and get 8 because they're not in the same direction. You also can't subtract them and get 2 because they're not in exact opposite directions. So what can we do? Let's start with the same tip-to-tail method. I'm first drawing the red vector, and notice that the end of the vector, or the tip, starts the beginning or the tail of the blue vector. Now I connect beginning of red to end of blue to represent my resultant vector, and if you look at it, this forms a right triangle. So I would use Pythagorean theorem to find the value of the resultant vector, the hypotenuse, and I wind up with 5.83 meters. To find direction, which is also important for vectors, we want to consider this triangle as being in the center of our north, south, west, east grid. Notice that this vector points between north and east. We'd want to use our trig functions to find the exact value, 31 degrees, and because it's connected to east, we're going to state that this angle is north of east. Let's look at an example problem. Here we've got a student walking 20 meters south and then turning and walking 25 meters west. The goal is to find the exact location that the student would wind up relative to where they started. If you want to pause the video and try this on your own, I'll talk you through all the steps here in a minute. All right, first thing we want to do is draw our vectors out. I start with a vector of 20 meters directed south. At the tip of this vector, I'm going to start my second one, which would be 25 to the west. I want to connect the beginning of the first to the end of the last, and that would be my resultant vector. I'll call this vector D. We don't know the length of that quite yet. Let's put this at the center of our XY coordinate grid. You don't have to draw this out every time. I just think it's a good visual as you're getting better at it. First thing we want to do is try to find the magnitude. I have two sides of a right triangle. I'm trying to find the hypotenuse, so I'll use Pythagorean theorem, and I find that my magnitude is 32 meters. Next is to find direction. I'm going to use my trig functions, specifically tangent, because I know the opposite and adjacent sides. The answer comes out to 51 degrees, but because it touches south, I'm going to state this degree measurement as west of south. So the exact location of the student relative to their starting point is 32 meters at an angle of 51 degrees directed west of south.